Okay, so we're back with chapter 12, which is there are two more chapters after this that I will record videos for. This chapter is on mostly the violin family. Um, I might kind of go off on tangents into talking about the other uh, stringed instruments. I don't know quite as much about harps, but guitars and violins and the violin family I'm familiar with. Um, I played viola for about 10 or so years when I was in grade school. I started in like third grade, maybe it was 8 years. Started in second or third grade and finished in 10th grade. So I played for quite a while. Um, so I'm a lot more familiar with some of the intricacies of what's going on with the violin family because I was a string player. Guitars, they don't focus much on it in in the notes. There's definitely more in the book, if I remember right. The main thing that we're going to emphasize about acoustic guitars is that we have a different plucking, uh, a different way you pluck a guitar versus a different way versus the way you would pluck a violin string if you're playing pizzicato on a violin. I'll talk a little bit more about guitars, um, even from an amplified electric guitar perspective toward the end of the lecture. But if I remember right, in the homework, there's really only a question about plucking an acoustic guitar and whether it's the same or different from how you would pluck a violin. Again, harps I'm not super familiar with, but harps have different string lengths and I believe linear mass densities to accommodate the big range that you have on a harp. So we'll talk some about that as we go through this. Slide wise, there aren't that many slides, but I do have a ton of videos available for you this time. Some of them are fairly long, but um, you don't need to watch the entirety of them. Like there is a one particular video showing all the kind of vibrational patterns of the back plate of a violin. That thing's like 9 minutes long, and realistically, you could watch the first 30 to 30 seconds to a minute and get the idea of what's going on in that whole video. And some of the things are really only to illustrate the concepts that we have here that I'll kind of describe in detail. And you don't necessarily need to watch all of them unless you're just bored and want to. So, with that, we'll move into this. I actually have now that we're almost done with this, when I got my computer that I've been using to record videos, it came with a little pin that you can use to write stuff. And the only issue was it needed a quadruple A battery, and I didn't have one until I went to the hardware store for some other things this week, and now I have it, which might have helped for drawing stuff when I was trying to draw with the touchpad. But um, we'll see if I need it going forward. But now I have this tool now that we're almost done. So the main way that you would play something in the violin family is with a bow. Um, when we say violin family, we mean violin, viola, cello, and double bass. Now we'll see that they're not exactly constructed the same way, or we'll hear that they're not exactly constructed the same way in terms of um, how big certain things are on the instrument. Like a violin and a cello have very different kind of respective sizes, like body to neck and these types of things. Whereas if you were to compare a violin and a viola, they're pretty similar. It's just violas are a little bit bigger because they are a deeper instrument than the violin, and they need to be larger to project those lower notes. And also, typically, you just don't have as many violists, and so they need to be louder on a per instrument basis to kind of stand out in a little bit more in the mix of all those instruments. But regardless of whether we're talking about a cello or a violin, typically what you're going to be doing is playing with a bow. And here they're showing a particular string where we have this is the bridge node, and this is the node at the nut of the string. And what happens when you bow, and this is why when you play violin or something, if you've ever looked at one after someone's played, it's always covered with this white kind of powder. That white powder is something called rosin, which is basically just tree sap, and it's sticky. And the reason it's sticky and you coat your bow hairs with rosin is so that the string will stick to the bow, and you can pull the string along to actually vibrate the strings. Without rosin, you can still get a little bit of sticking between the hairs of the bow and the string because the hairs are fairly coarse, but it's not nearly enough grab to really vibrate the string well, which means it often sounds really thin because you're sliding more than grabbing. So what happens when you bow is the bow is moving over the string, and it's going to grab the string because of the rosin in the bow hair, and it's going to pull the string with it. So this is the direction of the bowing here, and it's pulling the string with it. Now, it kind of gives you maybe not as sharp of a triangle as it's showing here, but this is not a gentle curve. It is a triangle type input that you're putting onto the string, which means instead of this being a sine wave, it ends up being a triangle wave, which means there's harmonics in even the open string that you play on a violin. So you pull it along, and at some point, the tension on the string pulls back toward the natural position, stronger than the friction between the bow and the string can handle, and it breaks free of the bow and vibrates back toward the center. So you get back to equilibrium, but because it's moved back, it's now got speed and it overshoots and it comes back to this side. And that wave now is transmitting down the string. It bounces back, and at some point, once the string has bounced back, it's not moving in relation to the bow anymore, up and down. And so the bow grabs it again and pulls and repeats this cycle. And what this means is every time that the bow pulls, it's putting a little bit more energy in, a little bit more energy in. So the very first time that it moves and it slips, it's not going to be making that much noise. But when it comes back and it moves and it slips again, and it slips again, this triangle wave gets bigger and bigger and bigger, and that's what's going to lead into the attack of the instrument, because it takes a few of these bowstring oscillations before it's really making enough sound to really cause the instrument to project. I have two videos showing this. One from the perspective of the string, so you can actually kind of see the shape, and then one that's kind of showing you down the string from the bridge, so you can see how as the bow moves. So the first one just shows the bow, the string slipping and sticking with the bow. The second one actually shows the string vibrating, so you can see how the wave travels back and forth down the string, and how it takes a few cycles of this stick slip friction mechanism to actually create enough of a vibration where it's really, the string is really vibrating well. So there are two super slow-mo videos. They're just in black and white. They don't have any sound. The first one is really short. The second one is a little bit longer. So that is our mechanism for bowing the string. Now, when we build a violin, there are two plates. There's the top plate that's got the F holes, and then the back plate, and then there's the sides and all that. We'll get into this in a second. So the back plate of the violin is basically just one big board, and it's relatively smooth. The top plate of the violin has roughly the same shape. It does have the F holes so that you can project sound out from the instrument. The size and shape of the F holes do kind of have an effect on the air resonance of the violin, because it makes the body of the violin kind of like a Helmholtz resonator, where we have an opening size and an air volume on the inside. So there's just going to be a natural air resonance to the cavity of the violin, and how you choose those F holes is going to change that tone a little bit. Also on the top plate of the violin, we have something called the bass bar. And the bass bar is it's a solid piece of wood that runs underneath the bridge up to the up under the fingerboard. And the point of the bass bar is to give that front plate a little bit more rigidity, and also to handle some of the vibrations from the bridge on this side of the instrument. The bridge here, if you've ever seen a violin bridge, which I don't have one image handy, there is a cutout to it, and the bridge is made to rock side to side with the vibrations of the string, because for the most part, the string vibrations in a violin are side to side. And so what happens is when the string is vibrating side to side, it's sitting in a little notch on the bridge. And so when the energy gets to the bridge and it's rocking side to side, it causes the bridge to actually move. So if I'm just going to draw this really badly, I'm not going to try to mimic the shape of a violin bridge. So it kind of has some feet on either side, and I'm just going to draw this as an oval thing, and it should be flatter up here. So when the strings are vibrating side to side, what happens is this whole bridge is going to kind of rock with those string vibrations side to side. And that's how the vibrations of the strings get coupled to the actual body of the instrument itself. On this side, that foot is resting on the bass bar, so that's going to naturally kind of make the whole front of the violin vibrate. And on the treble side, there is the sound post here, which rests very near the foot on the treble side, but not directly under it. And that is going to couple the vibrations from the top part of the body down the sound post to the back part of the body. Without your sound post, you actually would not really have a great sounding instrument, because you need both parts of the violin to vibrate strongly to actually generate enough power with the way the instrument is designed to really make it audible. If you did not couple to the back plate, then it just would not be a strong sounding instrument. You actually have some of the resonances, the key resonances of the violin body coming from this back plate itself. So if you don't couple to that back plate, you don't have those resonances there, and you're going to lose the power in the instrument. So our violin body has this kind of characteristic shape, and this is showing the top plate of the instrument. This is showing the back plate of the instrument. If you see here on the top plate, you can see where the F holes are positioned. Down here on the back, there are no F holes because we're talking about a solid piece of wood there. And what these different figures represent are the natural resonances of the top plate of the violin and the back plate of the violin. And the number above or below these are the frequencies of these resonances. And these are very highly tuned, at least in a good quality instrument. In a super cheap instrument that is probably just made very quickly on a CNC router in a factory and might cost you a couple $100, these are not probably as well tuned, which means you are much more likely to get a bad sounding instrument, because if these frequencies don't match something along these lines, then you're not going to naturally create the tone that you want out of the instrument. And so that is going to be a big difference in the quality of instrument, is how much time do they spend fine tuning these particular resonances of the top plate and the back plate. What these patterns are something called Chladni patterns. I have a video that's the really long one. It's like 9 minutes long, where a Italian school, they basically took a violin shape. It's a metal plate instead of a wood plate, and it's flat, which also changes because violin back is not flat. It's got curvature to it on the outside of the instrument and the inside of the instrument. So what you see in the video showing the Chladni patterns of the of a violin shaped thing are not going to look exactly like what you see here, nor are the frequencies going to be the same, but the general idea is pretty much the same. What you have is natural vibration frequencies that the body of the violin wants to vibrate at. So at 116 hertz here, where you see the white, that is basically an antinode, and where you see the black, that is a node. So the middle is vibrating strongly, and these edges are not vibrating at all. At 167, you still have the middle vibrating strongly. You have these kind of pieces that, instead of having the top to bottom vibration here, you now have these diagonal vibrations. And as you go up more and more, you get different and more complicated patterns. And these go even further than this 482. This is not the last one by any stretch of the imagination, which is part of why that video on the Chladni patterns is like 9 minutes long. On the top, you can see that the structures are similar. Here, this and this look kind of the same. This and this look similar, but not exactly the same. This and this look similar, but not exactly the same. The reason these are not going to be identical is because you have the F holes on top and you also have the bass bar over here. So that's going to change it a little bit. But one thing that's interesting to note is that they have tuned certain of these resonances to the same frequency. Both of these are at 222. Um, both of this one and this one here are at 403 and 404 respectively. Both of these are at 349. And so in a well-made violin, there's an attempt to kind of match these resonances of the top and back plates very well so that the instrument works as a unit instead of working against itself. So yeah, the video just on the Chladni patterns in general. There's also a second video showing a violin maker actually doing the method that they would to fine tune these resonant frequencies. And he shows that when he's making a violin or repairing a violin, he is going to reshape the back plate or the front plate, whichever he's working on at the time, to look for specific frequencies so that the violin sounds good. We'll see as we move on into this, if you get a really bad mismatch between these vibrational frequencies of the wood part of the instrument and the vibrational frequencies of the strings, then it just is not going to sound good. It's not going to radiate well, which means it's not going to be a powerful instrument. And if the mismatch is bad enough, you can end up with what we call wolf tones, which there's a video later on showing wolf tones on a cello. Wolf tones can happen on violins as well, but they're more common in cellos and violas and basses because the wood resonances of those instruments don't line up as well with the string frequencies as they do on a violin, which is part of why violin is designed the way it is, to maximize that coupling between the string vibrations and the body of the instrument. So this is showing holograms of the vibration patterns, but you can actually watch the video on the Chladni patterns and see how they do it, which is basically they just take some powder, and when you hit a resonance, it's going to basically, the powder is going to end up in certain regions of the instrument because of the vibrations, and you can use that to fine tune the shape of the instrument. So some fixed properties that affect the sound quality of these instruments are the bridge itself, the size, shape, mass, elasticity, placement. All of those things will affect it. Mass and elasticity, much like when we dealt with vibrational frequencies of mass on a spring, this is a kind of springy thing. If there's a lot of mass to the bridge, it's going to uh, be less resistant to those vibrations. And so it's going to require more energy to really move it around. The shape is very well defined, and you can kind of fine tune it to basically adjust the elasticity by removing material to make it more flexible, starting from kind of just a generic blank. Size can affect it because it's going to affect where the strings sit exactly on the instrument and how they are applying pressure to the top of the instrument. And the placement, this is specifically referring to like the placement of the feet. If you don't put the feet of your violin bridge in the right places relative to the bass bar and the sound post, you don't get that coupling of the vibration from the front of to the back effectively from the sound post, or it's just not pushing on the body of the instrument the way you need it to. And so you end up with not as good of a sounding instrument. It will be kind of weak sounding if you don't basically take advantage of the actual nature of the instrument. The body itself, your air cavity, remember that because of the F-holes and the fact that there is an air cavity in the interior of the instrument, it is a Helmholtz resonator, and that air cavity, how well it is tuned to the strings, vibrational frequencies can change the tone of the instrument. And the shape and thickness of the bottom and the top plate, that is adjusted to, again, make the instrument's wood vibrational frequencies match to the string frequencies as well as possible, at least in a good sounding instrument. Your material, the type of wood and the finish on the wood, this is not as important of a factor, much like when we talked about the finish of the not finish, but the material that you make a brass or woodwind instrument out of. It doesn't make that much of a difference because it's the shape that matters more than the material. This is kind of a similar idea. But if you're familiar with violins, you know there are Stradivarius violins, which go for millions of dollars anytime one hits the open market. And there have been many studies to try to see why these particular instruments sound better, at least to the listener, than other instruments. And there's been lots of studies, and some of them suggest, well, it's the particular wood they use, it's more dense than instruments of other eras, and so this is going to change it. The fact that anytime you're dealing with a acoustic string instrument where the vibrations of the wood itself, the soundboard, or in this case, the front and back plates of the violin, are creating the vibrations that actually will project the sound, the wood is going to matter to some degree. When we talk about something like an electric guitar, it's not that important because it's not the wood vibrations that are really making the sound. In a woodwind, it's not really the walls of the flute that are making the sound, so it doesn't matter what the walls are made of that much. What matters is the length and the shape of the air cavity that is actually creating the feedback and making the sound. So in this case, the wood is somewhat important. It's typically maple, if I remember right, in a violin. Especially the back plate is almost always maple, and flamed maple at that for visual reasons. Top plates may also be maple, but they might be something like spruce. I don't 100% remember right off the top of my head. And the finish matters here because if you put a really heavy kind of synthetic urethane finish on the instrument, it's going to impede how well it vibrates. And so finishes on violins are typically spirit finishes, and they are not really all that thick. They're very thin and applied in several layers, at least on good quality instruments. They're kind of a shellac type material finish a lot of times, but cheaper instruments will use something like a polyurethane finish, which can be fairly thick and again can impede the vibrations and kind of change the way that the body actually vibrates. So it's something that you can account for in the shape of the body cavity. If you know that you're going to put a thick finish on, you can shape your plates slightly differently to accommodate for the finish. But if you're just making them in a real kind of assembly line factory, that kind of craftsmanship may not be there, and so it might end up resulting in an instrument that doesn't sound all that great. And the strings are the last thing. It makes sense that the strings are something that that will end up affecting the sound. Now, with strings, there are really kind of three big groups of strings that go on violin family instruments. There are steel core strings, which are a steel wire that is then wrapped in aluminum or silver, um, typically, so that the string is smooth on the high strings, and on the low strings there's a bit more texture to them because you need the linear mass density to make those low strings uh, frequency low enough to get them where you need it. There are synthetic strings, which have a kind of nylon type material in the center, which are again wrapped with silver or aluminum to get the proper linear mass density and also the proper amount of tension on the strings when they are in tune. And then there are gut strings, which are again wrapped with metal, but the interior is made of, it's a lot of times you'll hear catgut, but it's always been something like sheep intestines. It's sheep guts that are dried out and wound. Um, the benefit to steel core strings, I have a short video which compares synthetic strings to steel core strings, is that they're very stable in tuning and they are often a brighter string. They're going to have more high harmonics. So if you're a player that needs tuning stability and life to the string, you typically would use a steel core string. Or if you just want the bright sound. So um, for a violin player that's typically a student, because their parents don't want to be spending a lot of money replacing strings regularly, so you put a set of steel cores on there, they last a long time. And they stay in tune very well, so they don't have to tune as often. It would be someone who wants their instrument to stay in tune. The video mentions like a pop violinist or a fiddle player, so that they don't have to tune quite as much when they're on stage. Also, fiddle players would probably want the steel strings just because the nature of playing fiddle, you tend to want that brighter tone to the playing style anyway. So those are what you typically see for people that play steel cores. The difference between a synthetic core and a gut instrument, a gut string, is not really all that drastic because both of these have a more pliable material on the inside. The synthetic nylon or the actual kind of gut center of the string are both less stiff than the steel string. They also are, because of that, much more responsive to changes in environment, typically temperature, but humidity also has an effect, especially on gut strings. Humidity does not affect synthetic strings as much, but temperature does, because the way that the strings expand with higher temperature is different than that of a steel string, which means they tend to go out of tune easier. But the trade-off is that the uh, they're kind of a mellower, darker sounding string. And that's typically what a classical player would prefer. They don't want this really bright, in your face sound. They want something that's a little bit mellower and darker to the tone. So a synthetic string or a gut string is going to give you that kind of sound. Synthetic versus gut, there's not really a big difference in the sound, though again, you're not looking at exactly the same material, so they're not going to sound exactly the same, but they behave similarly, which is why we've gone to synthetics. Um, Synthetics will last longer than a gut string because you're dealing with something that is not organic in nature. It's nylon. Um, the gut itself, if it gets exposed to moisture, is going to degrade. Um, I wouldn't necessarily say rot, but it's going to degrade. And so a true gut string, you get the same benefits as you would from a synthetic gut string, but you also have the added benefit that the life of the string is shorter versus a synthetic string. Now, it doesn't mean that some people still will not swear by anything other than true gut strings, but you pay for it. They're more expensive than a synthetic string. A synthetic string is typically more expensive than a steel core string. Um, and you get shorter lifespan out of it. So unless you have an unlimited budget or someone is buying your strings for you, you may not want to go the gut string route. You can go the synthetic route and get almost the same sound quality at a more reasonable, price effective, uh, cost effective range. They're still not cheap. Uh, I would say no violin or viola strings really that are worth anything are cheap. You can certainly get really cheap strings, but um, you have to be really careful with super cheap strings because they can put a lot of pressure on the top of the instrument and actually damage the instrument. Um, so you have to kind of deal with that um, that part as well. So some dynamic properties that affect the sound quality are the bow position. Um, there is a video that I have here showing um, a violin teacher talking about bowing in different lanes, and she shows all these different lanes, which is kind of a particular terminology to her teaching style. But lane 1 is basically right at the bridge, and lane 5 is over the fingerboard. And as you move from the bridge, at the bridge, the sound is very bright. There's a lot more harmonics in the tone, and as you move closer to the fingerboard, you kind of hit a sweet spot in the middle of the distance between the bridge and the end of the fingerboard. The fingerboard itself is not really anything more than a reference location. In this case, it doesn't matter how far the fingerboard extends for uh, the sound that comes out of the bowing. It's just a convenient place to talk about because you have the bridge and then you have where the fingerboard ends. Um, but in the middle of the distance between where the bridge and the fingerboard sit, and maybe slightly closer to the bridge, you get kind of this ideal location where you get a lot of power out of the instrument, and you also get a lot of richness to the tone without it being overly bright. Um, and then as you move to the fingerboard, you start losing power. And the reasoning for this is kind of twofold. I'll go back to the stick slip slide in a little bit and show you one of the things I'm talking about. But we'll talk about what's on this slide first. So if I am bowing at a particular, I'm going to draw something here. So say I have a string, just my string, right? And it has a note at either end, just like we've been dealing with anytime. So if I am, say, trying to play the string and I've got my second harmonic going on here, if I were to bow here in the center of the string, which you would never do, but if I were to bow here, I would make that harmonic unavailable, because I need a node here for the second harmonic, but if I'm bowing here, I can't possibly have a node at this location because I'm actually making the string vibrate there. And so this position at L/2, if I bow there, I can't play the second harmonic for this string anymore, because I'm putting energy in here, and now I've got an antinode there instead of a node. And so what ends up happening is I would be able to play the fundamental because I'm bowing right at the center of the string, but that second harmonic wouldn't be there. Now I'm going to kind of erase this. Let me draw a really bad third harmonic. So string, and this guy is what I'm going on here. So if I were to bow here at L/3, for the same reason, I wouldn't be able to get the third harmonic out of this. I would be able to get the fundamental. The triangle wave that I create here would give me the fundamental. It would give me the second harmonic in some amount, not quite as effectively, and L/3 would be gone. And so effectively what that means is where I decide to stick my bow and actually try to play the string is going to have a big effect on what actually comes out sound-wise. If I play at L/2, it's going to suppress my second harmonic, and the only thing I would really hear is the fundamental. If I play at L/3, it's going to suppress the third harmonic, which means I would hear the fundamental and the second harmonic at a lower amplitude, and so on and so on. So the closer to the bridge I am, the bigger N is, and the more harmonics that are there in the sound. So if I am as close to the bridge as I can possibly get, let's just say 100, L/100, I would have all harmonics from 1 to 99 available to play in some amplitude. And that would be a really bright, probably really annoying sound. If I move closer to the fingerboard, let's say I'm at L/6. At L/6, I would have 1, 2, 3, 4, 5. 6 would not be there. And that fewer harmonics would be a mellower tone, but it wouldn't be quite as grating because I would not be getting all those really high frequency harmonics in the sound itself. So picking a bowing position here, the closer you move to the bridge, the brighter and kind of richer the tone will be. The closer you move to the fingerboard, the mellower the tone is, and the darker it's going to be. Now I'm going to quickly switch back to this slide. Where you bow also is going to determine what goes on here. So if I were to bow dead center in the string, the amount of energy I would put into that vibration would not give me this big swing in the size that you have here. What would naturally happen is if I were bowing at the center, let me pull up this annotation guy again. If I were bowing at the center, instead of my dotted lines showing the kind of vibrational extent being that, it would be more like something much narrower, and that looks terrible, but it's hard to do this. So if the string is not vibrating as much, it's not going to be as loud. So as you move closer to the fingerboard, you kind of move past a sweet spot where you get this big swing and string vibration and a lot of power out of the strings, because you're just not moving the string quite as much side to side. So there is kind of a sweet spot in being able to do it. Conversely, when you're right at the bridge, you're trying to move that further, but it's not necessarily going to give you more power, because being right at the bridge means you're right next to a node, and that's naturally going to limit the kind of the available power you can put in, because the string still has some innate stiffness. So you want to be a little bit away from the bridge to get maximum power. And again, the further you are from the bridge, the mellower the tone, the closer you are, the brighter it is. So if you're right next to the bridge, not only is it bright, but it's not as loud as it would be as if you move a little bit further down the string. All right, back in here. So here is a little bit more with that. You have your fundamental here, second harmonic, third. This is just a refresher of what we had there. Remember that when we're dealing with violin strings, the different strings will have different linear mass densities and different tensions, which means the speed of the waves on these strings will be different. And that's what makes an A string different from a G string in terms of the sound, because the G string is a thicker string. It's also under less tension, so the frequency that comes out of it is lower. Because the effective string length for a violin is pretty similar for all the strings. The nut and the bridge are all pretty much at the same location, so the distance between our two nodes at either end of the string is pretty much the same for all the strings. So the only way we can actually tune the string is by changing the tension or the linear mass density of the string. And when you're actually physically tuning a violin string, you're typically changing the tension without a lot of change in the linear mass density. And that's how you adjust for small variations in pitch as the weather changes and things like that. So to get the best sound out of a violin, what you want are the natural resonances of the body, which is represented by these dashed lines. Wherever you have a peak, that's a resonance of the body, to line up with the frequencies of the strings themselves. So the top curve shows a good sounding violin and the bottom shows a bad sounding violin. The solid dots are wood resonances. So these are the body of the instrument itself vibrating, the actual wood. The hollow dot here is representing the air resonance of the body. So that's fairly well tuned to the D of a violin body, and probably on a viola. It may still be a D, but it might be the G on a viola. So the best sounding instruments will have these body resonances, whether it's a wood resonance or the air resonance, dead on the frequency for the strings. So this one sounds good. The G resonance is very close. The D resonance is pretty much dead on. The A resonance is very good. The E, maybe not so great, could be better. But at the high end, it doesn't get really, really obnoxious sounding. The bottom instrument here, the G is okay. The D is okay. The A is not even there. The E is better, maybe even slightly better than what you have off of this instrument. But you'll notice it gets really loud way up high here. So there's way too much high frequency response in this instrument. In fact, it overwhelms the where the strings actually are. And this would be a squeaky violin, which nobody really wants to hear. So all the tuning that they showed in shaping the plates of the back plate and the front plate of the violin body are so that these wood resonances line up well with the string frequencies, and you get a good sounding instrument that is powerful. There's also a how it's made video, which is a little bit more in detail for the whole thing, which also talks about some of the construction methods like the glues they use and purfling and all that stuff, which we're not going to get too in depth with here. So another thing you can do with really any stringed instrument, but in this case we're specifically talking about violins, are playing open string harmonics. So usually when you want to play a different note on a violin or a viola or something, what you do is you put your finger down on the string, push the string down to the fingerboard, and what you're effectively doing there is shortening the length of the string. So if the nut is normally here, and I put my finger down here so that now this part of the string is touching the fingerboard, now my string length is only from here to the bridge, and that shorter string length is going to give me a higher frequency sound as a result, because the speed of the wave on the string is the same, but now I've shortened my wavelength, and a shorter wavelength requires a higher frequency as a result. But we can play a trick, do a trick with the violin that we can, instead of pushing it all the way down to the fingerboard, we can rest our finger where a node for a particular vibrational frequency would lie. So if I were to put this dead center in my string and just not press down, but just rest my finger on the string at this position, I'm going to force a node at that location, which would then give me my antinode here and my antinode here, giving me the second harmonic for that string. I can do the same trick if I pick a position L/3, somewhere around here. I force a node at that location, and that would give me my antinode for the third harmonic. And this is, there is a video that shows this. You really only need to watch maybe the first minute or so of that, because she goes into other types of artificial harmonics that we're not really concerned about. We're just talking about what she calls natural harmonics. It's important to note that this is not, again, not pushing it all the way down. If I were to push my finger all the way down to the fingerboard here, I would get the same fundamental sound from it. However, it would be a more powerful sound. And the reason that you would play a harmonic like this is to get that higher frequency sound. And it also sounds a little bit airy, is really the only tone I can, ghostly kind of sounding. It's not as powerful. It's a little bit more breathy sounding. And it is very sensitive to position. If you're slightly off from this harmonic position, it's going to just sound bad because you're going to be activating a different harmonic. So it's very sensitive to position. It's something that I was never able to do as a player, because I just never got to that point to develop that skill. But it is something that is in the toolbox of especially someone who has been playing for a long time. There are definitely times where you want to do this versus playing just the natural note by pressing the string all the way down. So within the violin family, there's the violin, clearly. There's the viola, which in general is just a scaled up version of the violin. You make a bigger body, and you make the fingerboard is also longer. The biggest violins, you'll typically hear 15-ish inches. I think that's the nut to the bridge distance. Violas will go up to 17 inches, so up to a couple of inches longer just on the finger nut to bridge distance of the viola. And the reason that it's scaled up is just so that you can play those lower notes, because The strings on a violin are G, D, A, and E. On a viola, they are down a fifth. It's C, G, D, and A. And the bad thing about just scaling it up is that the wood resonances typically don't line up as well with the strings as they do on a violin. So the viola in general is not, without more fine tuning, is not quite as powerful an instrument in terms of effectively coupling the string vibrations to the um, body of the instrument itself. But because it does have a bigger body, it moves more air, and that kind of compensates for it not being quite as efficient of a body as the violin, but it can be loud as well just because it moves more air in general. Um, then you've got the cello. If you were to try to scale up a violin to the size of the cello, you would end up with a neck that wouldn't make sense in terms of the length, and also the bouts of the violin and the cello body don't have the same shape because strength-wise, the wood can't handle that shape. So the cello has a different proportion to it than a violin, and the body and string resonances don't match well at all. On the viola, they don't match well, but they're okay, I would say. Not great, but they're okay. On the cello, you really start to lose uh, that kind of match between the strings and the violins. And in fact, most cellos have a problem with something called a wolf note. And I have a video showing how you would find it on a cello, and they also make these things called wolf eliminators. There's different styles, but basically, what happens with a wolf note is that the uh, the cello body will have a resonance at a certain frequency, and when you get close to that frequency, the cello body itself trying to vibrate at that frequency in the string, it kind of gets bucked off, like dealing with um, a rodeo. Same idea. When that big cello body wants to start vibrating, it's not very hard for it to knock the string off frequency, and you get this really bad kind of beating tone. Remember beats from back when we were talking about two different frequencies that are really close but not exactly the same? It's the same idea here. You end up with the cello body wanting to vibrate at a certain frequency and the string not being quite there. And in fact, it's really hard for the string to hit that frequency that the cello body wants to be at. And so you just end up with this really bad sounding note. You can have them in violins, especially cheaply made violins and violas. They're more common than in violins. And in cellos, they're even more common than violas. So this is something that you have to uh, work around. Typically, you use a wolf eliminator, and what that will do is basically just temper the vibrations of the string so that you don't have that beating effect come into play. And with the double bass, again, the proportions are different, and so you have an even worse body string resonance mismatch than the cello. And so that's just the nature of the family. So violins and violas, pretty similar in shape. Cellos versus violin, different. Double bass versus violin, different. I can't remember if the cello and bass shapes are really the same because I did not play either of those instruments. By the way, the cello basically has the same string setup as a viola, just an octave down. And the double bass, I think, is different in that it uses fourths rather than fifths. But again, I'm not an expert in playing double bass, so I cannot, I don't remember exactly right now as I'm going through this what the strings are. But I'm pretty sure they're fourths instead of fifths. Or maybe not. I don't remember the strings for a double bass. Well, there we go. Tuning in a violin are fifths, G3 for the low string, then D4, A4, and E5. For viola, it's C3, G3, D4, A5. So you're down a fifth from the violin, and cello is down an octave from the viola. The double bass uses fourths instead of fifths, and you have E, A, D, G for the double bass. Now, when you are this slide is particularly referring to plucked strings for a violin. I'll talk a little bit about plucking for guitars because there's no slide after this, so this will be the part where I'm going to talk about guitars. With a plucked string, you are mostly dealing with the transient sound. You have a sharp attack from the pluck, followed by an extended decay, depending on how far you pluck the string and how readily your instrument is actually radiating away all that vibration energy. Actually, the bottom part of this is dealing with guitars. So if you are trying to pluck a violin, you want to pluck side to side because the violin bridge is designed to take side to side vibrations and couple that to up and down motion. So if you pluck your violin strings up away from the bridge, that vibrational energy is not going to be effectively transmitted down to the body of the instrument. And in addition, the pizzicato playing, you can do that stylistically because you might get some kind of slap on the fingerboard depending on how much you actually pull the string away from the fingerboard. But the most efficient sound is kind of a side-to-side pluck for playing pizzicato with your fingers on a violin versus an up and down pluck. For most guitars, the instruments are fretted, and so you're going to put your finger down, not necessarily on the fret, but very close to the fret behind it. So the string is resting on the fret and actually giving you a note at that location. The bridge on a guitar, rather than taking side to side vibrations and transmitting it up to down, it's fixed onto the soundboard of the guitar. So when you're plucking an acoustic guitar, anyway, you want that your pluck to be more of an up-down pluck to effectively get the sound to the soundboard of the guitar. So if you pluck side to side, it can take some of that vibrational sound and couple it to the soundboard, but it's not as efficient of a coupling. So typically, it's a stylistic choice. If you want the sound to be very powerful and direct, you pluck up and down. If you want it to be kind of in the vein of dealing with harmonics on a violin string, a little bit more airy, some side to side in the pluck will still give you some energy transmitted to the bridge, but not as efficiently because the string is still resting typically in some saddles. And so a little bit of the side to side vibration will still get coupled to the bridge, just not as efficiently as an up or down pluck. in playing an acoustic guitar, the top plate is often braced to deal with the string tension. Especially on an acoustic guitar that uses metal strings, there's going to be a fair amount of bracing because 6 strings pushing down on that top plate with a lot of tension would buckle the thin soundboard otherwise. On a classical nylon string guitar, you can get away with a little less bracing because the nylon strings are not putting as much tension on that front plate that's actually vibrating and creating the sound. Now, unlike a violin where you have that sound post directly transmitting sound from the vibrating top plate to the back plate of the instrument, that's not done typically in a guitar. And so you're actually relying on the air movement within the cavity to transmit those vibrations to the back plate and get some enhancement of the sound from the vibrations of the back plate of the guitar. Now, for an electrified guitar, you are not dealing with, well, let me stop there. If you're dealing with an acoustic guitar that is being played with electronics, you can use kind of a typical electric guitar pickup if you're playing with strings that are magnetic, like steel strings or some cobalt strings or something along those lines. But what's typically done is either a piezoelectric or a microphone pickup. So you will have either a small microphone that is under the bridge so that you can record the sound coming from the instrument, or what's called a piezoelectric pickup, which is a piezoelectric material is one that creates a voltage when you put stress on it. And so you put the piezoelectric material directly under the bridge, and as the bridge kind of presses on it, that is going to give you a voltage that you can amplify and then send to an amplifier or a mixing console or whatever. Those are your typical methods to take an acoustic guitar sound and turn it into something that you can amplify. As it stands, most acoustic guitars are very efficient at creating sound, and so you don't really need that unless you're just in an environment where you can't hear a single acoustic guitar just because of the nature of the room itself. Now, true electric guitar pickup it's less sensitive to the direction of the vibration, because what you have going on with the pickup in an electric guitar, you have magnets that are creating a magnetic field, and the strings are made out of a material that is magnetizable, typically steel or cobalt the string is typically mostly steel, but it may have some coatings on it that are also other magnetic materials. And so as the string vibrates through that magnetic field and gets magnetized itself, it changes the magnetic environment around it. And as we saw back in our chapter on electronics, when we were talking about microphones, if you change the magnetic flux through a coil of wire, you get a voltage out. Well, that magnetic environment that's created by the magnets and gets disturbed by the vibrating strings is picked up by that's why we call it a pickup, by a coil of wire that is surrounding the magnets typically. If not the magnets itself, pole pieces that are attached directly to the magnet. And so by winding a coil of wire, I'll just draw this. Oh no, I don't know where I put my drawing guy. Okay, so if you are dealing with, you look at an electric guitar pickup and you have these either screws or metal pieces. I'm just going to draw a handful. So let's say you had a weird 3-string guitar. So you have those pole pieces. Around this is a bunch of really thin wire. And so when the strings, if my string rests here and it's vibrating side to side, well, as it moves through that magnetic field, it's changing the magnetic field that this coil of wire sees, and then it creates a voltage. And so that's exactly all that's going on in a pickup, an electric guitar pickup, at least a typical electric guitar pickup. You just have one for every string. So if you play one string, you actually pick up the signal from that string. But of course, you can get vibrations bleeding across because of the harmonics and all that, which is why it tends to be a fairly complex sound instead of a really distinct single note sine wave type thing. But there's a lot of designs to how you pick this up. How strong are the magnets? How big is your coil? How thick or thin is your coil? All of those things will change how it sees that changing magnetic field and change the kind of characteristic tone to the pickup, which is why you look at something like a P90 pickup in a Gibson versus the single coil pickups on a Strat, and they sound very different because the design of those pickups, while similar in function, is very different in the way they decided to lay out their coil and where their magnets are and how strong their magnets are and all that stuff. Every little thing matters. The string also matters. How well does it actually disturb the environment? How close is it to the magnets? The closer you get to the magnets, the kind of more direct sound you get, but the more drag there is on the string, and so you have less sustain, but the sound is louder while it's vibrating. So you can get into a ton of complication in designing just a typical old magnetic field pickup for an electric guitar. And because of the nature of how the sound is created, it's just the interaction for the most part of the string and the pickup itself. You can make the body of the instrument out of almost anything, and it will still, if you put the same pickup and the same hardware, strings and everything, they'll sound very close. They won't sound exactly the same because there's always a little bit of an influence. If you have a plank of wood that will vibrate naturally with a certain note, it's gonna vibrate a little bit, and that's gonna change the kind of the dynamics of the sound some. But much like the the flute brass type body where it's more of a container for the vibration, again, this is not actually doing the vibrating itself. It's just something to house the pickup and something to hold the strings. And so for an electric guitar, you could make it out of a really expensive piece of really fancy wood, or you can make it out of really cheap, plentiful wood, which is what most of the instrument makers that make mass-produced instruments, Fender and Gibson, at least at the budget end, they're choosing wood that is readily available and easy to tool and may have some specific sonic qualities to it, but primarily it's easy to make, it's easy to kind of shape, and it's readily available and cheap, so that they can create a lot of instruments at scale cheaply, because the bulk of the sound comes from the string and the pickup and the hardware. So like you cheap out on the hardware, you kind of lose how effectively the string vibrates, and that's going to change the sound, which is why you can take a really cheap instrument and fix it up and make it sound better by changing pickups and putting better hardware on it. But there becomes a point of diminishing returns with all of that anyway. So yeah, you can make it out of really cheap materials like basswood, or you can make it out of a really nice block of ash wood, which is getting harder and harder to find cost efficiently. So you pay for it, but the improvement in the sound likely doesn't come from the better wood. It likely comes from the amount of detail that's paid to a $2,000 instrument versus a $200 instrument. Much like when you're dealing with a super cheap flute versus a silver flute that someone's put a lot of time and effort into fine tuning, you're paying for the attention to detail more so than the actual material that you're putting into it. At least for an electric guitar. For an acoustic guitar, it definitely matters what wood you pick. And you can design, pick different wall materials. You can deal with a solid piece of spruce on the top versus one that's kind of like a plywood construction. And those are going to sound different. If you're talking about like a solid spruce top on an acoustic guitar, it costs more than a plywood one because plywood is cheaper than solid spruce. And it's not 100% necessary that the solid spruce will sound better, but it does cost more to source that big piece of spruce that is flexible enough to serve as a soundboard of the guitar, the acoustic guitar. And so when you're talking about acoustically driven instruments, violin, acoustic guitar, in strings anyway, the material matters to a certain extent because the instrument itself is creating the sound. Once you get into something that is more of just a container for what is actually creating the sound, electric guitar, then it doesn't really matter what wood you put into it. Some will argue with me until they're blue in the face about that, but it matters some, but you can spend as much money making a guitar as you want to by choosing crazy expensive woods. But if you put the time into fine tuning it, you'll typically end up with something that sounds almost as good for a much more reasonable price than buying all this expensive exotic wood. So yeah, I've kind of rambled a lot there. Most of this is not really something you need to worry about. The things that matter from this slide really is that guitars and violins, because of the way their bridges couple the string vibrations to the body of the instrument, guitars get the best coupling out of plucking up and down versus violins get the best coupling out of plucking side to side. So guitars and violins, even though you can pluck both, you would typically pluck them differently to get the best sound out of each of the two instruments. Trying to remember if I missed any of I think toward the end, I have a quick simulation that is like a JavaScript simulation that should run in your browser so long as you have JavaScript enabled, where you can pluck a string at different positions and see how that affects the harmonic content. It's very similar to what's going on with bowing. If you are putting energy in at a certain location, you cannot have a node there. You have to have an antinode. And so any harmonic above that is not really effectively displayed. So on the simulation, if you go and you play with that, you can see if you pluck at the center, you basically just get the fundamental. If you pluck about a third of the way up the string, you only get the fundamental and the second harmonic. If you go a quarter of the way, you get the first, second, and third, and so on and so on. You get a little bit more because of the triangle nature of the string, but that's really all that one is showing. And then there's just like a slow-mo video of strings vibrating, which honestly, on a guitar, which doesn't show that much, but it shows a little bit in terms of how the vibrations transmit. Though the guy is plucking side to side instead of up down, so it's not, because if I remember right, the video has sound, but it's not the sound of the strings being plucked. Then it really doesn't matter whether he's trying to get sound effectively out of it or not. So yeah, this one was probably longer, even though it was only 10 slides, 12 slides, just because I know a bit more about these types of instruments than the others. The next chapter is dealing with also another stringed instrument, which is piano. Pianos are more complicated in many ways, not just because of their keyboard, but they play their notes very differently, and you have to tune them differently because of the range involved. So when we go through the piano, I will kind of talk about the evolution of the piano, because it's changed quite a bit. It started out as something called a clavichord, was like the first really keyboard instrument. And then you have something like a harpsichord, and then early pianos, and now kind of the modern piano, which they're all a little different in how they actually, how they're played. So we'll talk a little bit about the evolution. We'll talk a little bit about the mechanism for how the keyboard actually strikes the strings on a piano. We'll talk a little bit about how they stretch tune, and then what the pedals on a piano do. I have not played piano, so I don't know quite as much about that. Coming at it again from more of a theoretical perspective. But that chapter's also pretty short, so it will probably be a much shorter video than this. And I'm planning to record that in the next couple of days and get that up maybe midweek. The next test, if I remember right, only covers up to the string chapter. So pianos and percussion instruments, which are the last two chapters, are not on the next test that is coming up. They are on the final, but they're not on the next test. Next test is chapter 9, 10, 11, and 12. So this is the last chapter that you have to have done before we take the third test. And that's really about all I have to say. Just reminder to keep on the homework. I'm recording this on a Sunday, and I think chapter 9 closes today. I have extended the kind of the date to where it will be accepted to 5 days out instead of 3 days out, unless it's going to interfere with a test. And I'm not enforcing any late policies. So even though the due date may technically be on a Tuesday, as long as you have it in by Sunday, it will not count against you. I'm not enforcing any late policies on anything like that. Now, after it closes, it's a different ball game, because the answers become available. And I'm thinking about a way to maybe kind of give you the ability to replace a couple of the homework grades if you've missed some for whatever reason, but it's still in the very early stages, and I'm not promising that at this point. I will be creating a little mini assignment. It's mostly a completion thing, so I do want you to spend more than like 3 seconds on it, to kind of replace the in-class quizzes that we can't really do anymore since we don't have class. So that last 5% of the grade will be coming from this little mini assignment. It will be in Canvas. It'll basically be like pick an instrument and then talk about in very vague detail. You don't have to spend all the time like I was talking about electric guitar or something like that. Describe how it takes vibrations and turns it into sound. And that's basically it'll be broken down into a handful of questions, like what is vibrating? If you're talking about a violin, a string is vibrating. How do those string vibrations get to the body of the instrument to then make the sound loud so that it's audible? That kind of thing. There'll probably be like 3 or 4 questions in Canvas as an assignment, and I'll probably set it up as a quiz, but it's technically not a quiz. And as long as you complete it and spend a few minutes to 15, maybe 30 max on it. I'm not expecting like a 10-page report or anything. You'll probably get the 5 points. I basically want you to do some work for those 5 points, but I basically want to just give them away since the situation is what it is. So that will be coming soon, probably this week, later in the week, maybe around the same time as I post the piano chapter. I'm working on it. So with that, I don't really have much more to add, and I'll go ahead and end this up. So have a good day.